Let's talk about some more machine learning techniques. And one of the fundamental concepts behind machine learning is something called TrainTest. And that lets us very cleverly evaluate how good a model that we make in machine learning is. So let's learn more about that. Let's talk about machine learning, and specifically the difference between supervised and unsupervised machine learning. We're getting into the interesting stuff here, so let's go. So what is machine learning? Well, if you look it up on Wikipedia or whatever, it'll say that it's algorithms that can learn from observational data and can make predictions based on it. Sounds really fancy, right? Like artificial intelligence stuff, like you have a throbbing brain inside of your computer. But in reality, these techniques are usually very simple. And we've already done this, right? If you look at regressions, we took a set of observational data, we fit a line to it, and then we could use that line to make predictions. So by this definition, that's machine learning, and it's pretty darn simple. And yeah, your brain works that way too. So, it's kind of fun to think about, are there any insights in these algorithms into how your brain actually works? Maybe there is. Maybe underneath it all, there's really a very simple thing going on in there, but that's a topic for a different course. So let's talk about the two different types of machine learning we talk about, supervised and unsupervised. Sometimes there can be kind of a blurry line between the two, to be honest, but the basic definition of unsupervised learning is that you're not giving your model any answers to learn from. You're just presenting it with a group of data, and it tries to make sense out of it, given no additional information. So for an example, let's say I give it a bunch of different objects, balls and cubes and sets of dice and whatnot. And I have some algorithm that will cluster these objects into things that are similar to each other based on some similarity metric, okay? Now, I haven't told it ahead of time what categories certain objects belong to. I don't have sort of a cheat sheet that it can learn from where I have a set of existing objects and my correct categorization of it. It has to infer those categories on its own. So that's an example of unsupervised learning, where I don't have a set of answers that I'm letting it learn from. I'm just trying to let it gather its own answers based on the data presented to it alone. Okay, so the problem with that is that you don't necessarily know what the algorithm will come up with. So if I gave it a bunch of these objects on this slide, is it going to group things into things that are round, things that are large versus small, things that are red versus blue? I don't know. It's going to depend on the metric that I give it for similarity between items primarily. But sometimes you'll find clusters that are surprising and emerge that you didn't expect to see. So that's really the point of unsupervised learning. If you don't know what you're looking for, it can be a powerful tool for discovering classifications that you didn't even know were there. We call that a latent variable. So some property of your data that you didn't even know was there originally, but unsupervised learning can tease out for you. So an example, let's say I was clustering people instead of, balls and dice and whatnot. And I'm running a dating site, and I want to see what sorts of people tend to cluster together. Are there some attributes that people tend to cluster around, that they tend to like each other and date each other or whatever? And you might find that the clusters that emerge don't conform to your predisposed stereotypes. Maybe it's not about college students versus, middle-aged people or people who are divorced and whatnot, or their religious beliefs. Maybe if you look at the clusters that actually emerge from that analysis, you'll learn something new about your users and actually figure out that there's something more important than any of those existing features of your people that really count toward whether they like each other. So that's an example of unsupervised learning providing useful results. Okay, another example, clustering movies based on their properties. If you were to run clustering on a set of movies from like IMDb or something, maybe the results would surprise you. Maybe it's not just about the genre of the movie. Maybe there are other properties like the age of the movie or the running length or what country it was released in that are more important. You just never know. Or we could analyze the text of product descriptions and try to find the terms that carry the most meaning for a certain category. Again, we might not necessarily know ahead of time what terms, what words are most indicative of a product being in a certain category, but through unsupervised learnings, we can tease out that latent information. Now, in contrast, supervised learning is a case where we have a set of answers that the model can learn from. So we give it a set of training data, in this case, that the model learns from, and it can infer relationships between the features and the categories that we want, and then apply that to unseen new values and predict information about them. So going back to our earlier example where we were trying to predict car prices based on the attributes of those cars, that's an example where we are training our model using actual answers. So I have a set of known cars and their actual prices that they sold for. I train the model on that set of complete answers, And then I can create a model that I can use to predict the prices of new cars that I haven't seen before. So that's an example of supervised learning, where you're giving it a set of answers to learn from. You've already assigned categories or whatever to a set of data, and it then uses that to build a model that it can use to predict new values from. So how do we evaluate supervised learning? So the beautiful thing about supervised learning is that I can use a trick called TrainTest. And the idea here is, what if I were to split my observational data that I want my model to learn from into two groups, a training set and a testing set? So when I actually train my model, when I build my model based on the data that I have, I only do that with part of my data that I'm calling my training set, okay? And I reserve another part of my data, and I'm going to use that for testing purposes. So I can build my model using a subset of my data for training data, and then I can evaluate the model that comes out of that and see if it can successfully predict the correct answers for my testing data. So you see what I did there? I have a set of data where I already have the answers that I can train my model from, but I'm going to withhold a portion of that data and actually use that to test my model that was generated using the training set. Okay, so that gives me a very concrete way to test how good my model is on unseen data, because I actually have a bit of data that I set aside that I can test it with. And you can then measure quantitatively how well it did using R² or some other metric like root mean squared error, things like that. And you can use that to test one model versus another and see what the best model is for a given problem. You can tune the parameters of that model and use TrainTest to maximize the accuracy of that model on your testing data. So, great way to prevent overfitting. There are some caveats. You need to make sure that both your training and test data sets are large enough to actually be representative of your data. You need to make sure that you're catching all the different categories and outliers that you care about in both training and testing to get a good measure of its success and to build a good model. You have to make sure that you've selected from those data sets randomly, so you're not just carving your data set in two and saying everything left of here is training and right of here is testing. You want to sample that randomly because there could be some pattern sequentially in your data that you don't know about. But fundamentally, it is, like I said, a great way to guard against overfitting. So if your model is overfitting and just going out of its way to accept outliers in your training data, well, that's going to be revealed when you put it against an unset scene of testing data, right? Because all that gyrations for outliers won't help with the outliers that it hasn't seen before. Now, TrainTest isn't perfect. You can get misleading results from it. Maybe your sample sizes are too small, like we already talked about, or maybe just due to random chance, your training data and your test data look remarkably similar. They actually do have a similar set of outliers, and you can still be overfitting. Who knows? And you can see in this example, yeah, it can happen. So there is a way around that too, called k-fold cross-validation, and we'll do an example of this later in the course, but the basic concept is you do TrainTest many times. So you actually split your data not into just one training set and one test set. You split your data into multiple randomly assigned segments, k segments, that's where the k comes from, and you reserve one of those segments as your test data. And then you start training your model on the remaining segments and measure their performance against your test data set. And then you take the average performance from each of those training sets models results and take their R² average score. So this way you're actually training on different slices of your data, measuring them against the same test set, and that way if you have a model that's overfitting to a particular segment of your training data, that will get averaged out by the other ones that are contributing to k-fold cross-validation. It'll make more sense later in the course, but I just want you to know this tool exists for actually making TrainTest even more robust than it already is. So let's go and actually play with some data and actually evaluate it using TrainTest.